Hey kiddos, happy lesson number 4. Um, Last class we took a look at Newton's universal law of gravitation and how we can use it in combination with um, our understanding of circular motion and centripetal forces to calculate things like orbital speeds. Okay, today we're going to look at how gravity impacts the motion of orbiting objects. So we'll look at something called gravitational potential, compare it with gravitational potential energy, and what the pattern is for those on a planetary scale. Spoiler alert, it is different than what we expect on a scale near the surface of the Earth. Okay, and then we'll take a look at escape velocity. So what is required for an object to escape a planet's gravitational pull? And then we will use our understanding of Newton's universal law of gravitation, again in combination with our understanding of circular motion to derive Kepler's third law of planetary motion. Something that will be helpful for you all to have available to you is that either your textbook, the front cover of your textbook has all of those distances like the radius and mass of the Earth, the radius and mass of the Sun, Moon, and the distances from the surface of like the Earth to the surface of the Moon and stuff like that. And then take a look at last week's video if you can't find where that front cover is located on the digital textbook. Okay, it's in the drop down menu for all the chapters. Scroll all the way down and you should be able to find appendices and see that front cover. All right, so let's take a look at gravitational potential energy on a planetary scale here. I'm going to zoom in to my lesson. So gravitational potential energy on the surface of the Earth, we use GPE as mgh, right? So here on the surface of the Earth, the further you got away from the surface of the Earth, right, as measured by height, the more gravitational potential you have. But we know from our understanding of Newton's universal law of gravitation, right? Whoops, I want a different color. Right, where mg on the surface of the Earth is the force due to gravity. Okay, but on a planetary scale, the force due to gravity depends on the mass of the planet, the mass of, our gravity constant, the mass of the planet, and the mass of the smaller body near that planet, and it decreases in an inverse squared relationship with how far that object is away from the center of that planet, right? Their separation distance, center to center. Okay. All right, so we can see that on a planetary scale, the force exerted decreases, right? But here on the surface of the Earth, where the gravitational field strength is essentially the same everywhere, significantly on the surface of the Earth, the gravitational potential energy increases on the surface. So that's a little bit counterintuitive. So let's take a look at this graph, right? Where here's an object that has a mass m, and there's a gravitational force exerted downward, and gravity is doing some work. So remember, work is force times distance, right? Where here, the force is due to gravity, and the distance is r, right? The distance from the center of this object down to the center of the Earth. Okay. So as we get closer and closer as we get closer and closer to the Earth, right, the work done, as we get closer and closer to the Earth, the work done is more and more. So the work done by gravity as the satellite falls towards the Earth increases. Okay. So as we decrease the distance from the large mass, right, the Earth, we are increasing the gravitational potential energy. Right? This is opposite from what we experience on the Earth's surface. Right? The closer we are to the Earth, the more work is being done, the more gravitational potential energy we have, because the force exerted between the mass and the Earth is increasing. Right, so on a planetary scale, we are increasing an object's gravitational potential energy as we get close and closer and closer to the Earth. Okay, so to show you that that's true, let's derive gravitational potential energy on a planetary scale. Okay, so let's say this is the Earth, right, our big M mass, and let's say this is our smaller object, little m mass, and we want to put them so far apart that they're not significantly interacting with each other so that their gravitational force is effectively zero. And that distance between the two of them, to make that true, and actually I'm going to erase this because I want that distance to be clearly indicated from center to center. For gravitational force to be effectively zero, we're going to call the distance from center to center infinity. Okay, and then we're going to grab this mass and we're going to pull it in closer to the big mass. All right, so again, here is our planet, our capital M mass, and we're going to bring this M in closer, some distance, little m, right, so that they do have a force due to gravity that we can calculate using Newton's universal law of gravitation. Okay, and we're going to call this distance, instead of little r, we're going to differentiate it from this one. I'm just going to call it capital R, right, because it's going to be a specific distance. If we use little r as a generic distance from center to center, we can call this specific distance that they're apart capital R. All right, now how much work is being done by gravity bringing the mass in from infinitely far away into this specific position? That's going to be how much gravitational potential energy is gained. And we can use that to calculate the gravitational potential energy that exists between these two masses at this location. All right, so we've got Fg equals big G mm over r squared, where we know that the work done by gravity is force times distance. Okay, now we are going to do a little calculus. Don't be scared. You don't need to know how to do this, but those of you who are calculus folks, this is just justifying the equation that I'm going to end up giving you. Okay, so the amount of work done is going to be, right, if we make a graph of gravitational force over distance for these masses as they come closer and closer together, it'll be like an inverse relationship where if you take the area under the curve from infinity to r, that will be the work. that's done by gravity, right? The area under a force versus distance curve is work. Okay, so what we're going to do is to find the area for a nonlinear function, you have to take an integral. Okay, right, so that curvy S thing, some of you have been calling it, and we're going to go from infinity to capital R. And that integral is going to be gravitational force, which is gm little m over r squared, right? The change in force over distance, and the distance that's going to be changing is with respect to that r, right? The distance center to center. Okay, so that's going to be our integral here. And when we do that, we're going to end up with the work done is equal to negative big G m over capital R. Okay, actually I'll zoom out like this. And so this is the result of our integral. This is the area under the force versus distance curve, and what this represents is the gravitational potential energy that mass m has after it has been brought in from infinity to a separation distance of capital R. So GPE equals G m over R, and this is the generic gravitational potential energy equation for an object near a larger mass and a certain distance away from that mass, and that works for anywhere in the universe. All right, now we said that little g is gravitational field strength. We also have an idea that we don't use actually very much related to gravity, but we do use the idea of potential a lot when we talk about electricity. And this is a field forces unit, so we're going to compare two different field forces, electric and gravitational. Okay, so I need to introduce this idea of gravitational potential for comparison to electric potential, if that makes any sense at all. So gravitational potential, which we'll abbreviate as capital V with a little g subscript, is a ratio of the work done per kilogram of mass. Okay, it's just a ratio. So if I said, if you knew the gravitational potential, V, right, you could, and you knew how much mass was existing a certain distance away from a planet or something, you could figure out how much work would be done on that mass itself, right? So the work done is minus G m over R, right? The work done by gravity, the change in gravitational potential energy, over mass. These little m's cancel, and we get negative G mass of the planet over R. Okay, so again, gravitational potential is the work done per kilogram of mass. It's a ratio that we can use to predict how much work would be done on a specific amount of mass. And it is equal to negative G, big G, universal gravity constant, times the mass of the planet an object is near to, times the separation of their centers. Okay, and this is in units of, work is in joules, mass is in kilograms. Okay, all right, and we're going to compare that to an idea related to electricity.